Hello and welcome to the course series on basic cognitive processes. I am Dr. Ark Verma from IIT Kanpur. Today we'll begin to talk about various approaches to visual perception. In particular, I will talk about J.J. Gibson's approach to perception. But before we begin with that, let us talk about why do we need to discuss these approaches to perception in the first place. The key question in perception basically is what is perception really meant for? Why do we need to perceive the world, and what benefits does it give us, and what is our perspective towards perception as a cognitive function? The question one might ask is, what is the goal of perception? Is it for action or is it for recognition? I can actually illustrate the difference between action and recognition by just throwing a ball at you, and you'll probably first take evasive action. You'll try and save yourself from being hit by the ball, then really recognizing that what was this object that I threw towards you. This kind of tells us that we look at the world, we are interacting with this world, or we're perceiving this world more importantly to interact with this. Not really merely just to get a visual description of the environment we live in. That's also useful, and that's also something which perception is there for. But there is this debate between what is the actual use of perception. Is it for interacting with this world, or is it for just having a visual description of this world? Okay, we are talking about visual perception more specifically, but such a question can also be asked for other modalities of perception like auditory perception, tactile perception, and other kinds of perception. There's already evidence for the fact that perception for action and perception for recognition are actually different processes, and they basically involve different regions of the brain. This was the research done by Milner and Goodale in around 1998, and a lot of papers and a lot of experiments after that have actually confirmed this idea. So if you have this in background, and if you really try and look at the last lecture in this series, we were talking about representation and what is a representation meant for, and why do we construct representation, basically how do we construct representations, then you'll come to a actual difference between the way perception can be constructed. Say for example, weather perception depends on bottom-up processing. That is basically the flow of information through the perceptual system starts from the bottom-up sensory receptors and works upwards until an internal representation of the object is formed, or the flow of information through the perceptual system starts from pre-existing knowledge, like your memory stored in the brain, and then it moves downwards towards evaluating whatever sensory inputs you're getting. So these are the two routes we discussed yesterday about how mental representations are constructed, and this is in that sense actually one of the critical questions in how perception can be looked at. We'll talk about one of these very important theories of perception put forward by J.J. Gibson, and this theory of perception is called the ecological approach. We'll talk about why ecological in a short while, but let us say, suppose that the visual perception is primarily based on bottom-up processing of information. Okay, so whatever mental representations of this world you are going to construct will be basically built out of whatever sensory experience you're getting. J.J. Gibson actually believed that this is how we perceive this internal world, this external world, and he said something to the order of, when the senses are considered as a perceptual system, all the theories of perception become at one stroke unnecessary. You don't really need to specify the analytical processes. It is no longer a question of how the mind operates on the deliverance of the sense, or how past experience can organize this data, or even how the brain can process the inputs of the nerves, but simply how is information picked up from this external world via these senses. So J.J. Gibson basically believed that the mental representations that we construct in perception are entirely made out of the sensory experience that is delivered by each of our senses. We are talking more specifically in this sense about visual perception. The Gibsonian approach concentrates on the information present in the visual environment rather than how the brain or the mind operates upon it. An important component of Gibson's approach is the link between perception and action. He believed that action, rather than the formation of internal description of this environment, should be seen as the endpoint of perception. Gibson also conceptualized the link between perception and action by suggesting that perception is direct. In that the information present in the light is enough, is sufficient to allow a person to move through and interact through the environment. So it does not really need any kinds of intermediary processes or transformations to happen. It's just that the light that actually falls on your retina is sufficient to give you enough information to do both, get the description of the world and to be able to interact with it. He thought that perception could never be fully explored through laboratory experiments, and one of the reasons was that if you see a picture like this, it is still at the end of the day a picture. It does not carry all the information that if you have kept the real object would carry. Okay, so he kind of emphasized on this difference, and he said further that and because of this importance that he gave to the real world, and because of the emphasis he placed on conducting real experiments, his approach was called the ecological approach. He referred to theories that were based on artificial experiments employing these two-dimensional shapes as theories in the air, while he referred to his own theory as a ground theory, because he was actually conducting experiments in the real scenario, and interacting with real objects and looking at real scenes, etc. As it emphasized the role played by the real and textured surface of the ground in providing the information about the distance, that is one of the reasons why his theory was called the ground theory. The most important concept in Gibson's approach to perception is this concept of the optic array. The optic array basically is the structure that is imposed on the light reflected by the textured surfaces in the world around us. That is basically what this optic array contains of. The basic structure of the optic array basically is the light reflected from the surfaces in the environment, and that light converging at a point in space that is occupied by the observer. So imagine myself sitting in this room, and I'm actually, there's a lot of light in this room. This light is reflecting from the screens, from the cameras, from these walls. So all of this light converging, towards my eyes is basically what the ambient optic array is about. You can see this figure. This kind of demonstrates an observer sitting in a particular room and light reflecting from various surfaces in the room and then converging on the point in space where this observer's eyes are located. But the observer is rarely static. We are not really always sitting. We are actually moving. We are moving our head. We are moving our eyes. So this is also something that Gibson took account of, and he said that because of these sources of motion, the position of the head with respect to the eye is always altered, and the optic array also changes accordingly. So here is the demonstration of the fact that, say for example, if this individual is now standing, or say for example if this individual is walking in the room, the structure of the ambient optic array would change accordingly. Now, the primary structure of this optic array, what is this? The primary structure of the optic array is basically a series of angles that are formed by the light reflecting from various surfaces in the environment towards your eyes. Say for example, an angle may be formed between the light that is reflected from the near edge of a table, or from the far edge, or from the the top of the wall, or from the bottom of the wall, different ways. In addition to this primary structure of the optic array, Gibson maintained that there were additional higher order features that could also provide information, unambiguous information basically regarding the nature of the environment. So all of these different structures also tell you and give you rich information about the environment in which you are moving around. He referred to these higher order features as invariants, things that do not really change because those could be things that are static, and he believed that an observer could perceive the surrounding world by actively sampling this optic array in order to detect invariant information. So if you're actually at a place in the room, you would get particular information about the surroundings, about the objects in the room from examining these invariant features as well. An example of an invariant feature was explored by Sedgwick in 1973, and this invariant feature was a horizontal ratio relation. What is horizontal ratio relation? Horizontal ratio relation basically it specifies that the ratio of how much of an object is above the horizon to how much of an object is below the horizon is always constant as the object either travels towards or away from the observer. So suppose I'm standing at this end of the room, there's somebody standing at the far end, and the person is moving towards me or the person is moving away from me. This ratio of how much of this person is above the horizon versus how much of this person is below the horizon is going to be constant. This form of invariant information allows us to judge the relative heights of different objects and people regardless of how far away from us they are. This proportion of the object above the horizon increases with the overall height of the object. Let us see a picture which will explain you this. So here you can see people of same heights and as they are actually from at different distances from us. So in the first figure it's just near us, then in the second figure it's 1 meters away from us, and the third it's 10 meters away from us, and in the fourth one it's around 20 meters away from us. You see that this relationship is changing, but the ratio is constant. Here you can see people of different heights at the same distance, and you can again see that this horizontal ratio relation is constant. Now, another important source of invariant information in Gibson's theory is the texture gradient. What is the texture gradient? There are three forms of texture gradient relating to density, perspective and compression of these texture elements. Texture is supposed to be the exact nature of say for example of different surfaces. How does one surface differ from another? Say for example, in a carpet the elements are caused by individual twists of the material, the threads with which the carpet is made up of. On a road, the texture is basically formed by these small stones that are combined to make up that surface. So that is basically what a surface is about, and that is the idea of what texture means. Here you can see, for example, you can see, in the bottom you can see pebbles on the beach. In the middle you can see probably a tarred road. In the top you can see how a carpet is made, or maybe a shawl or something like that. In making use of these texture gradients, we assume that the texture of the surface is uniform. So you make this assumption that the entire surface will have the same kind of texture, and then you use this information to make judgments about what judge about different things from the surface. Let us take an example. The surface of the road consists of stones similar in size throughout its length, and therefore any change in the apparent nature of the texture provides us with information about regarding the distance, orientation and the curvature of the surface, that is the road. Imagine, say for example, you're riding a bike and you're actually on a very nice road made with similar size stones, and in a long distance you might notice that sometimes the road appears to be converging or it appears to be diverging, and this information about distance, if there are no other cues available, can actually be really important for you to guess how far you are from a particular milestone and those kind of things. We'll talk about this in more detail as we go ahead. So what we do using these texture gradients, we can actually tell if a surface is receding, that is moving away from us, or if it is actually coming closer. Let us take this example. If you see the texture of these tiles here, you can see that the tiles closer to us, say for example, appear much bigger. The tiles which are farther from us appear slightly smaller. We know for a fact that all of these tiles, all of these square boxes are actually of the same size. So we're using this information about the size of the tiles to actually make a judgment about whether which part of the tile is closer to us or which part of the tile is farther to us. These kind of things are used very cleverly by painters to create illusions of distance, etc. In a similar way, the perspective gradient and the compression gradient, so perspective gradient is the width of the individual elements, the compression gradient is the height of the individual elements. Both of these can reveal about the shape and the orientation of the surface. I'll take another similar example. You can see towards the right side, everything is slightly compressed, the width is reducing, so you get an information about the perspective, and say for example you can get the information about the shape, and if you see in the left side of the image you can get the perspective about the orientation of the surface. Okay, so you're using this information present in the surface to actually judge about the nature of the surface, or actually more importantly about your position in relation to this particular surface. Now, another important concept in Gibson's ecological approach is basically this concept of flow. Gibson says that what is clear to me now that was not clear before is that the structure, as a frozen structure, is just a myth, or at least it's a limiting case. Invariants of structure do not really exist except in relation to variance. Okay, let us try and understand what he's trying to say here. He's saying frozen structures, static structures are not really the thing. We are always moving, or objects in the environment are mostly moving, and in that sense, to have this concept of motion and how this motion changes, your relationship to, the different surfaces, etc., or objects in the environment. So motion is an important aspect of the visual world by virtue of which the environment changes over time, or the way you see the environment changes over time. There are two basic forms of movement: motion of the observer if you are moving around, and motion of the objects within the environment. Suppose you're sitting in a park and a lot of children are playing. Suppose you're actually standing in the balcony and you see a lot of vehicles moving by. Motion of the observer tends to produce the greatest degree of movement, as the entire optic array needs to be transformed. So if you're moving your head, if you're moving yourself, then whatever the angles of that are contained in this light, with this light reflecting from so many surfaces and so many objects in the environment, all of this needs to change at once. If, say for example, the objects in the external world are moving, minute adjustments with relation to those particular objects might be needed. Now, Gibson suggested that this transformation, if you're moving, provides valuable information about the position and shape of surfaces and objects in this external world. For example, an interesting cue could be information about shape and position that is revealed by something called motion parallax. Now, what is motion parallax? Very simply, motion parallax is basically the principle that the further an object is from an observer, the less it will appear to move. As the object comes closer to us, the motion of the object becomes more pronounced. You're put in charge of a moving train and you're looking outside of your window and you're trying to make sense of the environment around you. You're passing by a field and you look at a herd of cows grazing in a large field next to the railway line. The cows near the track will appear to move past much faster than the cows at the back of the field. Okay, it's not really necessary that those cows are running and the other ones are static. It's basically because you're moving faster and the cows, which are nearer, that is why they appear to move past faster. Thus, this degree of apparent motion is directly related, to the distance of this object from the observer, of the cow from the driver. You can see this figure here. You can see that if you're passing by and you're looking at your left, you're seeing that this flow is from the left to the right, and you're looking at the field. You probably you'll find out that the fourth cow, which is furthest, will appear to be not moving, even irrespective of whether it's moving or not, and the cow which is closest to the observer appears to be moving much faster. A second means by which observer motion can provide information about the shape and position of objects is through occlusion. Occlusion is basically when something is hid or occluded by something else. Okay, so imagine the same observer, the train driver that is traveling past the same field of cows, and the motion will cause the cows nearest to pass in front of or occlude the cows grazing further away. If you go back to this figure, you will see that the second and the third cows, more towards the right, the third cow is actually slightly occluded by the second cow. This aspect of occlusion gives you an estimate of that the third cow is slightly further away from the second cow. This is something which you can actually make up very easily. So this allows the observer to deduce that the occluded cows are farther away from those that are actually doing this occlusion. Okay. Now, Gibson dealt with this motion of the observer through the reference to flow patterns in the optic array. So he says that there are patterns of flow in the optic array. Flow is basically just movement. Now, say for example, again coming back to this train driver example, suppose the train driver is now bored at looking at the sights. He's now looking. He comes in the front of the locomotive and he is just looking further in the direction to which in the direction in which the train is moving. Now this entire optic array will now appear to flow pass from the left to right, assuming that the driver looks out of the right hand window. Now when the driver is in the front, the flow patterns in the optic array will change such that the texture elements that information in the surface will appear to be radiating from the direction in which the train is traveling. Okay, so it will appear like, say for example, you're moving in a particular direction and all the light is diverging from that direction. This point furthest in the direction is referred to as the pole. So if you're actually moving ahead and you're looking right in front of you, you will see that there's a point called the pole and all the light is kind of diverging from it. Here is a figure which is demonstrating this. Okay, say for example, maybe the driver kind of comes at the back of the train now. The texture elements that will that appear to make up the surface in the environment will kind of appear to yeah, so this pattern, yeah, I talked about this already. So this pattern will completely get reversed if the guard at the rear of the train, if the guard comes at the rear of the train and is trying to look backwards in the direction from which the train had come. That will basically lead to convergence of this light, the convergent pattern of the array. So you actually now in this figure, you're moving away from this direction and you'll see everything is converging towards the pole. Okay, so if you just look at these figures, this one is when you're actually moving towards the pole. This one here is when you're moving away from the pole. Pole is any point at the furthest distance to the direction in which you're moving. Now, Gibson, he proposed a set of rules that linked flow in the optic array to the movement of the observer through this environment. If the observer is moving through the environment, you can deduce a few things by observing the flow in the optic array. These rules are basically, so if there is flow in the ambient optic array, the observer is moving. If there is no flow, the observer is not moving. That is understood. Outflow of the optic array from the pole specifies that you are approaching this point. Inflow to the pole specifies that you are moving away from a particular point. The direction of the pole specifies the direction in which the observer is moving. So if the direction is basically right in front of you, you're moving towards it. If the direction of the pole is at the back, then you're actually receding from it. A change in the direction of the pole specifies that the observer is now changed direction. Okay. Now, so this was about motion. This was about earlier we talked about perspective, horizontal ratio relation. So we've talked about how this ambient optic array changes, or how this ambient optic array basically is restructured in light of new information, with respect to the environment. Now Gibson, as I began saying, Gibson believed that perception is an act. It is an action, and it's not really merely a passive response. Okay, it is basically an act of attention. You choose and you select to attend aspects of the environment while you're not really concerned about all the other parts. Okay, so it's not really a triggered impression, it's an achievement, and it's not really a reflex. He is basically telling us that you're actively involved in perception. That is, you're looking for information with which or on which you will interact. This brings us to the concept of affordance. Gibson basically took this idea of information being picked up further by stating that the end point of the perceptual processes was not the visual description of the surrounding world, but rather that the objects would directly afford their use. So once you look at the object, there is enough information in light emanating from that object that will tell you about how to use that particular object. That is what Gibson actually meant. So at its simplest, the concept of affordance builds on earlier research done by Gestalt psychologists. We'll talk about them in due course. Basically, which says that features of objects actually provide information as per or regarding their use. If you see the door, the two surfaces of the door here, one of these surfaces has an handle. It affords holding it it affords taking a grip of it, while the other surface of the door does not have a handle, so it kind of affords you pushing through it. Okay, so you look at the surface, you realize how do you interact with the surface, and that is how you make out whether you will pull it, or say for example whether you will grip the handle, or you will just push the door through your palm. Again, different kinds of handles can afford different kinds of grip formation, and again this is basically also derived from the light emanating from these objects. So you automatically modulate the aperture of your fingers, and you try and hold these different figures. Gibson further claims that affordance acts as a bridge between perception and action, and that affordance does not require the intervention of any cognitive processes. So he says information information, or that is the light emanating from all of these surfaces, is enough for a person to be able to act and interact with the object, act on these objects, or interact with this environment. There is no role of memory in perception, according to Gibson, and he says that the observer does not really need to consult prior experience in order to be able to interact with the world. Okay, he says there is already enough information in the world, already enough information in the light that is being reflected from the world, the light that he called the ambient optic array. So he's strictly, this approach is strictly bottom-up approach. It's kind of building up from whatever the sensory experience is gained by your eyes. He says, for example, that the system resonates to the invariant information in the ambient optic array, meaning probably that global information about the optic array is dealt with by the perceptual system without the need to analyze more local information such as lines and edges. So he said this global information about this light reflected from these edges and the surfaces is more than enough. Now, that was mostly what Gibson was saying. Nowadays, experiments using dynamic naturalistic stimuli can be done, virtual scenes can be constructed, and images of brain activity while people are viewing these scenes or viewing these objects have also been captured in a way that would have been difficult to even think of in the time that Gibson was around. However, the stimulated lure of the screen should not really blind experimenters and theorists to this difference between the real scenario and the scenic scenario that you construct, that we construct in our labs. Okay, this is something you can take off from Gibson's analysis on perception. He says that there is much more information in the real world when you're actually interacting with the environment than if you're trying to study the process of perception by conducting experiments in our labs, where you are basically projecting these stimuli on two-dimensional screens. Now, to sum up whatever we've talked about Gibson, we've basically talked about the ecological approach, and we talked about how Gibson suggests that the light array from this external world may be sufficient to provide us with a rich source of information to really construct very rich mental representations of this external world. We also saw that Gibson actually emphasized that perception is more for action rather than just the description or recognition of this visual world. Thank you. In the next lecture, we'll talk about another approach on visual perception.